Hi there, thank you for clicking on this video. This is our practice set for operations on functions. Please like and subscribe, super fast to do that. If you find this problem set helpful, drop a comment or question to engage. Let me know what you liked, what you didn't like, anything that you feel needs more treatment so I can make my videos better. And please check out the many other videos and playlists on the channel. As always, pause the video to work these problems on your own and then come back to check your work. Okay, so this first set of problems is just practicing with that notation. And if you watch the lesson for this, which you should, the practice set is meant to go with the lesson that I wrote. One of the things that I mentioned was the notation for this is technically like f plus g of x, where you indicate like that this is the name of the function that we're trying to find, and this of course is the input variable. But if you need to, you can simply write f plus g, and that is a fairly common shorthand because we know from the rest of what's on the page what the variable is. So what I often will do, and I tend to go overboard when I am illustrating or explaining things. So what I would do personally for my own work and what I show when I am explaining things aren't quite the same thing. So for number one, I might do this if I were demonstrating it for students. And I would put the parentheses around it to emphasize like that we have two different functions and that the operation between those functions is adding, and that the parentheses in this case are cosmetic. And I would go through all of that. If I were doing this on my own, I would not bother with those parentheses because I know that they are cosmetic and that I don't need to do anything with them. Now it's simply a matter of combining like terms. So we have x to the third. I'm just going to kind of cross that off. We have a 2x squared that has nothing to combine with. Here we do though, we have negative 7x plus x. So that's negative 7x plus 1x, which will give us negative 6x. And then 1 plus 4 is 5. Okay, and that's our combining like terms. Now for 2 and 3, this is intended to emphasize one of the aspects of subtraction that was discussed in the video. So we have f minus g, so plus 1 minus x plus 4. And in this case, these parentheses are not cosmetic because you are grouping what you're subtracting together, and you have to make sure that you distribute that subtraction through. And so a little less extra work here. Now, what I would probably do if I were doing this on my own is I would skip this and go straight to this. But I usually do want to see the signs done out. Okay, now combining like terms, we have x to the third. We once again have nothing to combine that 2x squared with. Here we have negative 7x minus another x, which is going to give us negative 8x, and 1 minus 4 is negative 3. Now, if you want to, if you know how subtraction works, okay, instead of redoing that process, you could just do this. Say g minus f is negative x cubed minus 2x squared plus 8x plus 3, because when you switch the order of the subtraction, you flip the sign on everything. Now, I am not a fan of shortcuts. Okay, so I would rather, and you should too, if you are not sure of that, if that seems like math voodoo, like the magic happened, okay, do it out. So we have x plus 4 minus x to the third minus 2x squared. So what I'm doing here is I am making sure that I am subtracting everything in the parentheses. So minus x to the third minus 2x squared minus negative 7x which is to add 7x, and then minus 1. Putting this in order, we've got negative x to the third minus 2x squared. We have x plus 7x, which is 8x, and 4 minus 1, which is 3. And you can see that, yes, that matches what we got when we flipped the sign. Always so important that you know why things happen and that you are convinced that it is like a reasonable thing to happen. So don't go flipping signs, okay, if it feels like I made that up out of the blue, okay? Like no making stuff up out of the blue. Okay, here we have multiplication, and remember that you have to have, I mean, that's like a ginormous dot I got there. Closed circle, closed dot is what your subtraction means. You cannot have a bubbly open circle. That is something different. So for this one, we have f times g. So that'll be x to the third plus 2x squared minus 7x plus 1 times x plus 4. And I am a fan of the area model. Okay, so we're going to write that out. And then we have x plus 4. It is a nice compact way. You're not going to miss any of your multiplications. So x times x to the third is x to the fourth. This will be 2x to the third minus 7x squared plus x. Here we have 4x to the third plus 8x squared minus 28x plus 4. So you're not going to leave out any of your multiplications, and your like terms are very often, 100% of the time, but very often going to be on those diagonals. So we're going to have x to the fourth plus 6x to the third plus 1x squared. You can, of course, just say x squared minus 27x plus 4. Okay, and there's our multiplication. Now, for the division, I mentioned in the video that I will often have my students just leave it as is, but it is not going to hurt us to review our division. This one is divisible using synthetic division. So if that is your preferred method, you might have done that. Again, I am in favor of the area model because of its flexibility and versatility, and the fact that the way we're going to do the division is going to use the same kind of model that we just used on the multiplication. So in this case, we use the degree to determine how many columns we have, but if you misgauge the number of columns, it's totally okay. You can add columns if you need them, or if you end up with extra columns, you just like, I gave myself too many columns. This is the thing that we're dividing by. And what we are dividing, this expression here, is the one that goes on the inside. So just like when you're multiplying, you have the base and the height, and you're looking for the area. When you're dividing, you have the area, and you're dividing it by the height, and you're looking for the base. And so this x to the third is the result of x times something. And so we have to figure out what that is. So that would be x squared. And then the model works the same way. So just how when you're multiplying, you multiply the base and the height, each little chunk of it, to get the cell, we do the same thing here. So we have a 4 and we have an x squared, which gives us 4x squared. But then we need to come back up here and say, all right, so I've got a 4x squared, but remember the area only allows for a 2x squared, which means I've got too many. I've got to subtract 2. So we got to subtract 2x squared. So now 4x squared minus 2x squared gives me 2x squared. So we're happy. This negative 2x squared came from doing x times something. In this case, negative 2x. And then 4 times negative 2x is negative 8x. But this only allows for negative 7x. So I've got too many negatives here. I'm going to have to add something. X times 1 gives me 1x. And then this cell right here comes from doing base times height. So 1 times 4 is 4. And we have a little bit of an issue because the area is supposed to be a 1 and I have too much. I have a 4. So I would need to subtract 3 and that's the remainder from my division. So this would be x squared minus 2x plus 1 minus 3, or you could say plus negative 3 over x plus 4. So nice review of the division there. Again, you can do that other ways, but I like to stick with a model that's going to work for factoring, work for multiplying, and work for dividing, and work for all the things. All right. Now, for these ones, we are looking at domain. And so what is important to do at the outset here is to figure out what the domain of these functions is that we're like coming into it. So remember, when you are taking the domain, looking for the domain, you're looking for all the possible x values. And when you are taking a square root, that can't be negative, okay, because that will generate an imaginary number. So x plus 3, whatever x plus 3 is, has to be greater than or equal to 0. Okay, it could be equal to 0. We'll subtract the 3, and that lets us know that x is greater than or equal to negative 3. So that's the domain on the first one. Our second one, this is a line, so the domain is all real numbers. Okay, so finding the domain. Here we go. Good times. So we have f of x plus g of x is what we got going on there. So we have x plus 3 square root and then x minus 1. And the domain of the resultant will be whatever works in both. The G, everything works, but not in the F. And it's got to be able to work in the F. So the domain is going to be what is carrying over from the F. So the domain is x is greater than or equal to negative 3. Now it gets interesting. So f divided by g. So this would be the square root of x plus 3 over x minus 1. And so this one has an issue where you've got the original restriction, but the operation, that division, introduces like something else that might happen. And we know from knowing our operations that that can't be 0. And so we have x minus 1 cannot be equal to 0. Go ahead and add the 1. So x cannot equal 1. So how on earth do you write this as an answer? Excellent question. Well, there's a lot of ways you can write it. I'm just going to put it this way. I'm going to say x is greater than or equal to negative 3 and x cannot equal 1. So I'm going to write it that way. There are other ways you could write this. I don't know how much I want to get into the weeds with that. But if you were to look at this, like here's the negative 3, and it can be greater than or equal to the negative 3, except when x is equal to 1. Right there, when x is equal to 1, you got to have an open circle, okay? It's got to go over that open circle. So it could be something like this, negative 3 to 1, and then 1 to infinity. Like that, where you've got the cutoff down here at the negative 3, and then also are creating an open space there at the 1. There's other ways that we could do that, but if you came up with that, good job. Okay, last one here. This one, we've got G over F. Okay, so now like this is no problem. Okay, so that's all real numbers. Now we've got this issue where again, like this cannot be equal to 0. So that's not a huge deal. Okay, so no 0. So what that means is that now you cannot have x plus 3 cannot be equal to 0. And so what that does is it changes, if we come back over here, where it could be greater than or equal to 0, we are no longer allowed to have the or equal to 0. Okay, cannot be equal to 0 anymore. And so what we're left with is just the domain is x is greater than 3. So it's got to be greater than 3, greater than or equal to 3 to keep the square root positive, but the equal to 3 has to go, or equal to negative 3. Yeah. Negative 3. Yeah, the negative 3 now has to go because now it's going to interact with being in the denominator. Now, if the 7 and 8 there, if you found those challenging, that is 100,000 bajillion% okay to find those challenging. They are. You've got to reason and think your way through it. Getting things partially correct, that is totally okay when you're learning how to do this. So if you caught like the 1 but missed, oh no, the square root, like, just give yourself some space to be able to learn and to get better at it. And the next ones that you see, like, you approach them fresh. All right, number 9, graph number 5 on Desmos and describe what you see happening in number 5. And just for the record, well, it's going to pop up. So let's take a look. So that's number 5. Okay, so this is, now you could have graphed this before or after the division. So this is f of x divided by g of x. And when you're looking at that negative 4, okay, because this is where we have that restriction, like we're not allowed to divide by 0. So you've got this x plus 4 in the denominator, but that is not allowed to be equal to 0. Therefore, x is not allowed to be equal to negative 4. So the point of this exercise was to go and take a peek at what is happening. And so you've got like this over here, and it's kind of doing its thing, and then it seems to like go up into oblivion, and then it picks up down here. So what I want you to notice is that you do have a break in the graph there. Okay, there is a break in the graph. So there's 2 pieces, and those 2 pieces are not connected. We have not seen that before, at least in the Algebra 2 sequence of lessons that I've been recording. I've not seen that. Now, what exactly is going on there? So what I did on the next visual is I actually graphed this vertical line, x is equal to negative 4, and I made it dashed, okay, and so that we could see it. And what you see going on there is right when x is equal to negative 4, you see these 2 pieces of the graph that appear to be like vertical lines almost, or they look like they're becoming a vertical right at that negative 4. So that is actually, there's a vocab word for that. And I'm going to throw it out here. And I did have a question. I actually changed the last question on this when I typed it. Was for you to look up that word. Just go and look it up, okay? It's asymptote. Lots of consonants going on at the beginning, S-Y-M-P-T. Like a weird combination of consonants there. So yeah, so go ahead and like look that up. That is for a future unit, but it's good to like just kind of take a look and investigate like what's going on there. If you've got that still up on Desmos, go on over and like kind of run your mouse over the graph and see what the x values are doing as you get closer and closer to that line. Now for this last one, explain or show why switching the order of subtraction always flips the signs of the terms. So this is, and if you go back to the original problem, like I had kind of like a encouragement, making an argument is less about like constructing a flawless argument, at least like at this, if you were in a college class and you were asked to prove something, you would need to make it airtight. But for most students, the value of this exercise is in just reasoning your way through it, just like getting some reasoning. So here's how I'm going to reason it. Okay. Now I'm going to start with a few numerical examples, and maybe you thought to do that. Okay, so if I have 7 minus 3, that's 4. If I have 3 minus 7, that's -4. And we can see there that when we subtract or switch the order of the subtraction, that we flipped the sign. Suppose I have 1 minus 6, okay, that is -5, and 6 minus 1 is +5. So you might start with just doing some numbers, play around with some numbers and see, like, when I switch the order of the subtraction, do I always flip the signs? And where this came from was, like, if I have, if I go back, well, I don't want to go back to the problem, but we saw it earlier where, like, when we have big long strings of things that are subtracting, we just flip the signs of everything. So what I'm going to do here is say, suppose f of x is equal to a and g of x is equal to b. Okay. F minus g. What I want to know is the same as, I'm not doing this like I had it done out. I actually have it done out in my notes and I'm trying to freeform it, and that's never a good idea. So we want to show that if I do a minus b, that is the opposite of b minus a. In other words, like, when you switch the order of the subtraction, do you get the same thing except negative? Okay, so switch the order of subtraction, you get the same thing but negative. Okay, so watch how this works. A minus b, so I'm going to distribute that negative, so that's going to be negative b plus a, and adding is commutative, so I can switch the order, so that'll be a plus negative b, and that's literally the definition of subtraction there. Ta-da. Okay, now if you wanted to, you could maybe do this with more terms, okay, but essentially if you had more terms in it, it would always come out the same way. So I don't want to get, like, yeah, it could get like really messy, but if we did like a plus b minus c plus d, is that going to be the same as negative c plus d minus a plus b? So in that case, what I did was I like made it two terms. So we have first one minus second one, and then if I switch the order of it, like, is that the same as it being negative? Well, this, you just distribute the negatives. Over here, you'd have c plus d minus a minus b, and now we're going to negative all of that. So negative c minus d plus a plus b, and now you can see that that's just a matter of switching the order. So how you wanted to explain that or demonstrate it, up to you. The point of the exercise wasn't like, can I create this like absolute like flawless argument, but more, can I reason my way through this to get something that convinces me that this will always happen in every case. All right. So please don't forget to like and subscribe if this problem set was helpful. Comment below to engage. Let me know what you think. And check out the many other videos and playlists on the channel. I will link some below for you to peruse, and I hope to see you in a future video.